Hi, my name is Suraj Modi, and I welcome you to join my talk on enhancing system resilience with exponential backoff in distributed architectures. I'm a software engineer here at Uber, and I've spent quite some time working in the industry, working with high QPS, high performance requirement systems, which need to be highly available and need to have very low latency. The agenda for today's talk is first, I'm going to give you an introduction on what exactly is exponential backoff and set the stage for you to understand this concept. Then I'm going to talk about how to use it, some real world libraries that have support for this. And I'm going to then dig a little deep into the personal experience that I had when I used this technique to achieve very high availability and low latency in a critical system that I worked here at Uber. So to set the stage for you, let's take Uber Eats as an example. Let's say you're a user for Uber Eats. You open the app, and now when you open the app, it renders a feed on your phone. So that your phone is basically the client here, and the phone issues a request to a backend services, which is first intercepted by an orchestrator. The job of this orchestrator is to fan out the request to different data providers. Let's take an example. Let's say data provider 1 is a service which basically tells you for a given lat long or for a given geohash, what are the stores that I have in the vicinity? Data provider 2 basically tells you what is the orderability status of the stores. Can I place an order right now? Is it shut? Do I need to render it on the app? That is business logic that needs to execute on the orchestrator. And let's say there's a third data provider which tells you, okay, fine, what are the deals that are being offered in the area where I'm trying to place an order from? So a typical request response pattern would look like the client makes a request to the orchestrator reaches out to data provider 1, gets the set of stores that are orderable in the vicinity, then makes a request to data provider 2 to check its orderability status, and then sequentially or in parallel, I would prefer in parallel, figure out what are the deals that are available in the neighborhood. Imagine you make a request, orchestrator gets it, it reaches out to the first data provider, gets a response back, reaches out to the second data provider, gets a response back. But then when it reaches out to the third data provider, it gets an error. We have two choices here. Choice 1 is to fail the parent request entirely and ask the client to retry. Or alternatively, what we could do is the moment the orchestrator gets an error, it can make a decision to retry after a certain delay. Maybe data provider 3 is going through some garbage collection because of which we got a timeout. Maybe data provider is unavailable, so like some other reasons. In that scenario, the orchestrator decides to make the same request after a certain amount of time. And let's say we weren't lucky the second time either, and we get an error back. Based on the diagram, the orchestrator decides to make another request, and this time it's successful. Great. Orchestrator gets a response, processes it, renders the feed, and gives it back to the client. From a client's point of view, the client is not even aware of the fact that data provider 3 failed 2 times. Sure, maybe it takes slightly longer to load the feed because had data provider 1 given the response in the first the app would have rendered faster. But at the very least, we did not waste resources with data provider 1, data provider 2 fetching the same data again, and the latency that we incurred, the client didn't even notice it. How do we even use it? You can think about exponential backoff as a strategy that we use when you're trying to communicate with another upstream or a database, and then having some logic there which determines what do we do if we get an error. If we get an error, do we decide to retry or do we decide to fail the request? If we decide to retry, how do we retry that? In what frequency? How many times do we retry? And and in this process of retrying, is this an infinite loop? When do we decide to stop retrying and actually give back an error to the requesting service? As you can see, this is written in Rust, but this concept is ubiquitous. It is not language dependent, but some of the variables that we take when we're trying to retry is we take in the function that we're trying to retry. This could be a gRPC call, an HTTP call, a call to the database, and then we take in the maximum number of times that we want to retry this. There is, let's say we say in this example, we have a function, and then we decide to retry this 5 times. Then there's an initial delay, which basically tells us that, hey, I made a request, I got an error, For how long should I wait before trying the request again? Now, why do we want to wait? Maybe the upstream or the database is in a transient state where it can recover eventually. And then when we make another request, we actually get a successful response. So that's initial delay. And then we have the max delay, which basically tells us that for how long are we willing to wait before issuing another retry request. And then we have a jitter factor. So a jitter factor is basically telling us that, let's say we had a linear retry algorithm, like a linear backoff retry algorithm, where let's say the upstream service fails, we retry a request again after 5 seconds, fails, we again retry after 5 seconds, fails, we again retry after 5 seconds. But with exponential backoff, there it's a bit different. With exponential backoff, the first time we decide to retry after 1 second. But the second, and let's say if we get a failure, the second time we don't retry after 1 second again. We give it we try to increment the delay exponentially. And we also introduce a jitter factor so that, let's say if there's an upstream system which is being called by 10 people simultaneously, we don't have synchronized retries, because then all of them would be retrying at the same time, and then that would just mean like a waste of resources, and maybe the upstream would get into a state where it's very hard for it to recover from. Maybe the like instances start crashing. So the jitter factor ensures that every time we increase the delay duration, we add some randomness into it so that we avoid the situation of synchronized retries. And then the most important thing is a function which tells us the error code that we got back, is this even retryable? For example, let's say you try to look up for if the store is available or not. And for some reason, let's say the store does not even exist in the database. And then you get a 404 or like a not found. In that case, does it make sense to retry? It depends on like how you have written your application. Maybe you're working with an eventually consistent system and it makes sense for it. And it makes sense for you to like retry maybe a couple of times before actually considering this entire request, before actually failing this entire request. You would want to do that maybe if you're working in a system which is like eventually consistent, where you've written the store entry into the leader and it takes some time for the followers to catch up to it. And maybe the first 2 requests you get a not found, but then on the 3rd request, you actually get back the result. So this totally depends on like how you have chosen to implement your system, what kind of problem domain you're working on, and if a not found is retryable. On the other hand, let's say you get a transient error like unavailable. Is that retryable? That is more often than retryable, or that is more often retryable than not, because the system could be in a transient state where it's doing some like background work, or for whatever reason, because of like some network failures, it is unavailable at the moment. But when you retry, you may get back a response. So that's some snippet that I have here. And this technique can basically be extended to any programming language. Then moving on to the next slide. I briefly spoke about like some of the retryable error codes. So these are some of the common HTTP error codes that we could potentially see. And then, for example, if you get a 408, it's a transient network server condition, and that's why you would potentially want to retry. If you get a 429, which is too many requests, you're probably being rate limited. So it probably makes sense for you to retry after a certain period where all the other requests have been served. If you get a 500 internal server error, you may want to retry it. You may not want to retry it. It depends on how you perceive, how devastating do you perceive this error to be. If you get a 502, that's a bad gateway. It could be an upstream server issue. All these error codes, they are not prescriptive in any way. They're just like guides, as these are some of the error codes that you could potentially benefit from by retrying. But depending on your application, depending on like depending on like the nuances that you know about the systems, you may choose to retry other error codes, or you may choose to not retry some of these error codes. So to give you, and like I spoke about previously, there's a difference between linear and exponential. The whole benefit of doing exponential versus linear is with exponential, you get like faster recovery from transient failures because you're increasing the retry intervals towards the first. You can think about it as a window where towards the first few seconds of the window, you retry more often. And towards the later part of the window, you retry less often. And that way you're getting like more retries towards the initial part, and maybe you can recover from the error faster. And the other thing that I spoke about was synchronized retries, which we get if you're using, let's say, a linear backoff algorithm without any jitter, and if you're just doing the retries periodically, you're basically missing out on the opportunity to recover from the error faster, just because your retries are happening like at fixed intervals. Then talking about like some of the real world libraries that we have, which have support for exponential backoff. The Apache HTTP client that has built-in support for exponential backoff. Then there's some Elasticsearch client libraries, any kind of like a request response or database access library that you're using would potentially have support for exponential backoff, where you just tweak in the parameters. But even if they don't have it, it's very easy to write a wrapper which mimics this process of doing exponential backoff. But this is just to showcase like how ubiquitous this concept is, and like how libraries provide native support for exponential backoff. And then to give you some personal experience, I had to work on a system where I had to render the skeleton of a store. When I say a skeleton of a store, I'm talking about like in the Uber Eats domain. Uber Eats is also like venturing into grocery and retail nowadays. So let's say if you open a storefront, you need to figure out what does the storefront look like and what are the items that I even need to show. So the very first call, one of the data providers that we have is a tree, which tells us, okay, fine, this is the the tree is basically just a UUID tree, which tells us these are the sections that we have inside the store. Inside these sections, we have these subsections. And then inside these subsections, we have all these items that you can order. The first part is basically getting the skeleton. And the second part is then using the UUIDs to further hydrate what exactly those entities mean. So I was using a database which was built on top of MySQL, where we had requests in the order of hundreds of thousands. So what do I do in case the database fails or it gives me an error? So what I did was I utilized the exponential backoff algorithm. Previously, we did it without retries, and we could see that the service availability was pretty low because every time the database would give us an error, we would just fail the request, which would impact our success rate and availability. But then later on, when we incorporated exponential backoff, service availability went up to 5 nines, and while still being within the latency SLA of 100 milliseconds. And the best part was a realization that I came across was every time you get a request, you can think about it as the client giving you a budget. Let's say you get a request, and let's say it has a timeout of 5 seconds. You have a budget of 5 seconds, which you can use to serve that request. Now it's up to you how you want to use that budget wisely. It is crucial for you to understand that you need to respond within 5 seconds. And let's say one of your upstreams is not responding on time, and let's say you made the first request and you get back an error, you still have, and let's say all of that happened in the first 1 second. You still have 4 seconds left in your budget to make n number of retries and still be able to serve the request in time without failing the request in the first try itself. The trickiest part here, which you would ask me, is how do we even go about tweaking these parameters? What should my initial delay be? What should my max delay be? What should my number of attempts be? This is something which you can only realize with experimentation. So what I would often recommend people is to build a simple load test for the services that they're trying to integrate with, and then come up with these parameters that can be tuned by simulating requests, looking at like how the database responds, handling all these like different kinds of error scenarios, and then seeing what actually works best for you. What the numbers that work for me and the setup that I'm in may not be the best for you. And this is something that you discover with trial and error. And that is what I would say is the most complicated part of getting exponential backoff. Cool. So that's all I had for this talk. I hope this added some value and you learned something new. And thank you for joining, and have a great day.